Thanks a lot for deciding to spend 1 hour of your time on this session. I'll make sure that we achieve the target of understanding what we are going to cover in this session and probably introduce Hadoop to you. Let's talk about what is big data. We'll get into and then we'll talk a bit about what is Hadoop. We'll talk about what is Hadoop, and so this is part of the whole presentation that we typically do on day one. So we'll stop at what is Hadoop. Then in trainings we do cover what is complete ecosystem of Hadoop, and we do a deeper dive on HDFS and Mapreduce. Of course, we'll finally take up the questions. The course objective of this particular section is to introduce you to big data, to introduce Hadoop to you, explain how Hadoop works, get friendly with HDFS and Mapreduce, get aware of Hadoop ecosystem, and understand how Hadoop is used in the real world. So this is pretty much what we'll typically cover quickly. I think the most important question is not exactly what is big data, but real important question is why does it deserve so much of attention? Why on a weekend we all are getting together and discussing big data so much. There are serious reasons. As I say, the research from IDC shows that big data market will be $24 billion by 2016. Big data would create around 4.4 million jobs by 2015. And there is a shortage of around 200,000 big data professionals in the United States alone as of today. So we are not talking of a couple of years from now, we are just talking about as of today, there is a huge shortage. So either you're a professional looking for better career prospects, or you're someone who has a startup, big data is the place to be, because this is where a lot of opportunities are in. So what is big data? So in the simplest of terms, really simplest of terms, big data is any amount of data that one single physical machine cannot handle in terms of processing and storage. So even if you had, let's say, all the money, the best machine you could probably buy has 64 gigs of RAM and 64 terabytes of data storage, the max. And what data we are talking about is typically of scale of, let's say, hundreds and thousands of terabytes and at times petabytes of data. So one machine simply cannot cater to the amount of data you have. That's typically called as big data. So if you see, big data is the amount of data that is beyond the storage and processing capabilities of a single physical machine. So data that has large volume, comes from variety of sources, variety of formats, and comes to us with a great velocity is normally referred as big data. So now the idea here is simple. So far we've always been programmed to look at data from a perspective that, okay, it is rows and columns and data is all stored there and it's all relational, proper structure. But what big data talks about is that there is a lot of data that goes unanalyzed, which is not really in a relational format. Data that comes from Twitter, Facebook, data that comes from your weblogs, data that comes from your RFID sensors. So data can be of any format, and data that is getting generated at a great velocity. So that typically is referred as big data. So if you see, normally people talk about 3 V's of big data. So first is volume. So for data to be referred as big data, the volume of data has to be massive. The second point people typically talk about is variety, where for data to be referred as big data, generally the data would be semi-structured and may originate from variety of sources in variety of formats. So here we are talking about log files, XMLs, JSONs, and whatnot. Third is velocity. For data to be referred as big data, the rate at which data comes into the system is really, really fast. Take example of Facebook. In an hour, imagine the amount of likes, Facebook photos, and comments that happen. The amount of data that is generated is amazingly huge. So in a very crude way, let's visualize how big data looks. So you have a physical machine that has its own limitations, but the data is really, really larger than that particular machine. So that's volume. Second is data comes to you at an amazing speed. That's velocity. Third, data comes to you from variety of sources. That's variety. So that's typically 3 V's of big data. Now, over the past few months, whenever a lot of people would ask a lot of questions on big data during, when we talk about this section. I've taken few questions that are most logical that have come from my students, and I've compiled them to, basically integrate the missing pieces. So first logical question is, big data is clear, that's fine. But how does this data really look like? So the answer is that there is no defined set of rules which says, okay, this is how big data looks like. Big data can be any data that is from RFID sensors, web logs, climate sensor data, user interaction logs. This can be any data which is, which is semi-structured and is there for you to analyze it. Okay, what do we do with this data? Well, simple answer, analyze it. The tough part, what's the value of taking pain of analyzing this data? Well, in this huge heap of data, there are some golden nuggets that can really give you an unfair advantage in your business. Now take example, Amazon records all your browsing history, all your click history, and because of that, they deploy, they are able to, basically personalize the behavior in a better way. And most of the times, we end up buying stuff on Amazon that, we never thought of buying. So take example, you browse for a game once or twice. Now Amazon figures out that, okay, this is someone who's interested in games, and next time you see all the games coming in your face, and most of the times you end up buying it. Or along with that, they have this fantastic feature like people who bought this also bought that. So they've created this fantastic recommendation engine by analyzing this data which was lying not in a database but stuff like web logs and user interaction data. So this data appears to be as like log data, what value it could be, but it can really give you a lot of value. Next logical question, can we have some use cases of how world has used big data, how they've analyzed it and got value out of it? Identifying customers who are most important, identifying the best time to performance maintenance based on the usage patterns. Now, this is a fantastic case study for Rackspace, where Rackspace wanted to figure out when is the best time for me to perform a maintenance in a particular country. So what Rackspace did is they basically analyzed all their logs and came up with analysis that, okay, this country, this is the time I can bring down my system, and they really were able to achieve the minimum downtime because the usage was really less based on the timestamp. Third, most common use case, analyzing your brand's reputation by analyzing social media posts. So there's another, most common use case where these are utilizing big data. They are getting the data which is in their, in their databases for customers. Along with that, they are getting data from Facebook, Twitter, LinkedIn. They are mixing and matching this data to get interesting analysis from for the customer, and basically in turn they are able to serve customers in a better way. How can such huge data be analyzed? Now, one thing is clear, that we clearly said that, okay, one physical machine isn't capable of analyzing this data, so we need some way to basically distribute and perform our job. So as I said, as the volume is beyond processing and storage abilities of a single physical machine, some magical distributed way has to be used, that's for sure. So we need some distribution framework to take care of us. And the question comes, wait, distributed systems like MPI have been around for more than a decade. Since our college days we've been knowing about distributed systems. So do we even need to take this course further? Does the world really need another distributed system? The answer is yes, the world certainly needs another distributed system. And let's see why. Why world needs another distributed system and why existing system cannot be used. Now when you take an example of a typical distributed system, you will have a storage area network and you will have your application servers. Okay. So let's say you have a 10 terabyte storage, and you deploy 10 Java servers which will basically analyze the data. So you'll write your program, and each program will, let's say, analyze 1 terabyte of data. So if you see the flow, programs run on each app server. All the data is in storage area network. Before execution, each server gets the data from SAN. After execution, each server writes the output to SAN. So this is how a typical distributed system has been around, has been working for past decade or so. But then this particular model has some issues. So problems with a typical distributed system: huge dependency on network and huge bandwidth demands. So you run on your machine on run your code on 10 machines. Every time you run a code, 1 terabyte of data is transported basically from SAN to your local box. You analyze that, you write it back. So the amount of network bandwidth that is huge is amazing, and it's like network can become a real bottleneck. Scaling up and scaling down is not a smooth process. So when you write a program in a typical distributed fashion, you might you may be able to run it on 5 machines, but as soon as you want to go to, let's say, 100 machines, you will not be able to do that. You'll have to certainly change some part of your code to make sure that you're able to run your code. Third, partial failures are very, very difficult to handle in distributed framework. So take example that you have your 100 machines running. What if 88th machine fails? You're gone. Basically, the only way to take care is that the developer has to do something to make sure that the job restarts somewhere. A lot of processing power is spent on transporting data. If you see, major resources in terms of your processing are spent just on transporting data to and fro. Data synchronization is required during exchange. Now, to make sure that node number 1 isn't doing something that node 88 is doing, you need some way where each node knows what the other guy is doing. There's some kind of data synchronization that is required. So basically, if you look at it from a developer's perspective, you were set to write a small program that is for your business logic, but you are ending up taking care of so many things that aren't really related to your business logic. You need to take care what if something scales up, scales down. You need to take care of partial failures, and like it's a lot of pain for something that you aren't achieving out of. As a programmer, I should be just writing my business logic. So then whole world is in trouble, and Spider-Man comes to save. This is where Hadoop comes and saves. So this is what, so now the next topic we are going to talk about is how Hadoop really helps us out of this whole situation. So far we've covered problems with typical distributed system. We've covered what is a typical distributed system. We covered what is big data. We've covered why big data deserves your attention. And we've overall covered what is big data. Alright, so now we move to what is Hadoop. So Apache Hadoop is a software library. Apache Hadoop software library is a framework that allows for distributed processing of large data sets across the cluster of computers using a simple programming model. The simpler way to put it is, in the most simplistic terms, Hadoop is a framework that facilitates functioning of several machines together to achieve the goal of analyzing large sets of data. In the most layman terms, it's some magic where machines are working together to achieve your goal. So Google, now there's a slight history to it. So Google was really, the amount of data that Google had, they were really hitting the limit, and they wanted some way to, manage this whole thing. So they created a distributed framework inside Google. Now Google did not open source that, but they gave the knowledge to the community through white papers. So they published 2 white papers, and they explained how Google is handling so much of data. Once the white papers were released, a gentleman called Doug Cutting saw the white paper, and he decided to develop something similar in the open source community. So that's where Hadoop really started. So while Doug Cutting was developing the whole thing, Yahoo got interested in the project, and Yahoo recruited Doug Cutting, and they gave him a team to develop Hadoop. And after a couple of years, when Yahoo was running Hadoop in production, they made Yahoo open source to the community. So for Hadoop, a big applause for, actually we should be applauding Yahoo, because they took this brave step of open sourcing Hadoop and letting it in the hands of everyone. By the way, there's an interesting story that, so when Doug Cutting completed the development of Hadoop, he wasn't really sure what name he would want to give. So his baby had a yellow color elephant, and the baby would call that elephant as Hadoop. And that's how the name came, Hadoop. So the name has no meaning, it was short, sweet, and Doug Cutting liked it. But otherwise, yeah, there is typically no meaning to what Hadoop is. It's what his baby used to call his elephant, and that's how it is. So Hadoop consists of two core components. One is the HDFS, Hadoop Distributed File System, and the other one is Mapreduce. So we'll talk about them in detail. So a set of machines running HDFS and Mapreduce is known as Hadoop cluster. Individual machines are known as nodes, and a cluster can have as less as one node and as big as several thousand nodes. I think the biggest cluster right now is with Cloudera with 4,500 or 4,400 node cluster. Now let's visualize what exactly is Hadoop. These are multiple machines that take your big data. What they provide you is processing plus storage. So this is the easiest way to visualize Hadoop. Multiple machines working together to provide you processing and storage services of data that is really, really huge. That's Hadoop for you. Now digging a bit deep, what you see is Hadoop has one master node and there are multiple slave nodes. Slave nodes can be like thousands of slave nodes. Now on the side of master, the guy who takes care of storage is called as name node, and the guy who takes care of processing is called as job tracker. On the slave node, the guy who takes care of storage is called as data node, and the guy who takes care of processing is called as task tracker. So this is how Hadoop is structured. So if you carefully look, when you are on your basically on a client, be it you have a Hadoop client or something, where when you give the data, so you'll be providing data and program. So the first data would move to Hadoop and then your program will get executed. Let's look at it this way. So in step one, you will have all your data and you will give it to you'll pass it on to Hadoop. The data is passed to the name node and then eventually gets passed to all the data nodes. So this is how your data is right now inside Hadoop. Then you give your program and you give your program to the job tracker, the guy who's taking care of processing. The job tracker will then schedule the program on all the data that is there on the local node and it will give you the output. So what actually happens? Once you give data, let's say you have 640 MB of data, data is broken into input splits of 64 MB to 128 MB and the blocks are moved to different nodes. Once all the blocks are moved, the Hadoop framework passes the program to each node. Job tracker then starts scheduling the programs on individual nodes. Once all the nodes are done, the output is returned back. So this is how typically Hadoop works. So for Hadoop to be able to process the files have to be first put inside HDFS. So let's say you have files on your Linux box. You will simply not be able to analyze it using Hadoop framework because you'll have to first put those files inside your Hadoop file system. So HDFS is responsible for storing data on the cluster of machines. Data is normally split in the blocks of 64 to 128 megabytes and spread across the cluster. By default, each block is replicated 3 times. The replication factor can be lowered or increased based on your configuration choice. To ensure that data is not lost, similar blocks are always prepared on replicated on a different node. So this is how HDFS Hadoop Distributed File System works. So bit of HDFS basics. HDFS is closely based on Google's file system. It operates on top of a native file system, Unix file system, provides replicated storage using cheap commodity hardware. So HDFS is completely read-only, random writes are not allowed. Now see, when we are getting data, we are storing them in blocks of data and replicating them. It made sense that we just push the data inside and do analysis on top of it, but not let people update the data. So Hadoop performs best with small number of large files. We'll see that later. So it's the name node on the master node and the data node on the slave node that takes care of HDFS. For HDFS to be accessible, name node has to be up all the time because all the meta information is stored inside name node. So this is how it looks. Take example that you have a file called data.log and that has, let's say, 4 blocks. So it's broken into 4 blocks. The name node stores the metadata, that is, okay, this file data.log consists of these 4 blocks. And if you see, the storage is basically spread across the cluster and each block you see has been replicated 3 times. So today we have 3 machines. That's why each machine has 4 blocks. Tomorrow if we increase the machines by 6, each node will have 2 blocks. This is how HDFS works. So this is HDFS. Let's talk about Mapreduce. So Mapreduce is a data processing component of Hadoop, and it attains the task of processing by distributing the processing across the cluster. Task on each node processes data present locally. This is important. So each machine in the slave node is processing data, is having data node and task tracker. So task tracker will only typically operate on the local data. Mapreduce consists of 2 phases, map and reduce. And in between map and reduce, there is a small phase called sort and shuffle. Now, let's look at the easiest way to see what Mapreduce is all about. Now, assume that we have a file that has some text and it is named as data.txt. The goal is to count the number of times each word occurs. So assuming we have this text which is, hi, how are you, where have you been these days, where can I find you, and are you there? So the required output that we are looking for is hi once, how once, are 2 times, you 4 times, and so on. In Mapreduce, every input is viewed as key value pair. So in the above case, key is line number and value is the whole value of the line. So key by default is line number and value is the whole value. Now, hypothetically, this is how it works. So each line, which would be some input data, will be given to a map, and what map would do is it will count each word here. So if you see, first map takes hi, how are you, second takes where have you been these days, third where can I find you, fourth are you there. And this is how you get your output of map. After map, there is a small sort and shuffle phase where keys are actually sorted and all the values are brought together. So you see, how is 1, how is 1, r is 1, 1, u is 1, 1, 1, 1. So all the data from all the mappers is taken and it is consolidated based on the key. Later you write this logic of adding everything. So you get this input and you give it to the reducer. The reducer simply adds all that has its value. So you see, for each v in value, sum is equal to sum plus v. And this is what you get as an output. This is your final output. This is how Mapreduce works.
If the name node crashes, what happens?
Yeah, so as of now, in the existing version, there is something called as secondary name node, which will be covered. So secondary name node periodically takes the backup of name node, and as soon as name node crashes, you can restore it from the secondary name node. So there is no standby concept. You will have to make sure that you restore it again. And the one which is released right now, they have taken care of it by something, a concept called high availability, where you have two machines, two name nodes, and they are pointing to same data, and at one point one name node is there which is active and another is passive. As soon as the active dies off, the passive takes over.
And these slave nodes, do they all have to be in the same data center or same geographic location, or can they be just about anywhere? I mean,
yeah, they can just be about anywhere.
Okay.
Because everything is IP based. So if they are able to talk to each other, everything should be good. That's it.
And they could pretty much be any platform, right? Unix, Linux.
Yeah, they can have any distribution of Linux, but they'll not be on Windows typically.
Okay.
Go ahead.
When the data is like you are saying that it copied into the 3, like the minimum times is 3, and if that all the maps are working on the same data, like if it is copied into the 3 servers or the 3, and
no, there is one original copy and 2 duplicated copies. So Mapreduce is only working on the original copy all the time. Let's see how this will work. So I have 52 cards, and let's say we fire up, we write a Mapreduce program, and let's say we have 4 mappers. So map 1 will take any random 13 cards. Okay, let's look at the whole process. So we will hand over these 52 cards actually. Let's say look at them as like, okay, 52 different files. We'll hand them over to Hadoop cluster, and what Hadoop cluster will do is, let's say it will break them to blocks and perform the operations. So hypothetically, let's say we have 4 blocks of 13 cards each, and we will have 4 mappers. So mapper 1 will have 13 random cards. Mapper 2 has random 13 cards. And mapper 4 has random 13 cards. Now in their map phase, their only visibility is these 13 cards. So mapper 1 only cares about his 13 cards. He doesn't care about what mapper 2, mapper 3, mapper 4 has. Absolutely. Okay. And now this mapper operates on this 13 cards, and it takes one key value pair at a time. So it takes one card at a time and comes up with heart comma 1, heart comma 1, heart comma 1, spade comma 1, spade comma 1, spade comma 1, spade comma 1, diamond comma 1, diamond comma 1, club comma 1, club comma 1, club comma. So like this, each guy would come with his own set of data, and this is where your map phase completes. So now all mappers will have their own respective values for this. Then you have a big sort and shuffle phase. Now what happens exactly in sort and shuffle is all the keys are brought together. All the keys are brought together. So we have sort and shuffle. After sort and, so basically from all mappers, the data starts traveling to the sort and shuffle phase, can be at one machine. And finally what we typically get from sort and shuffle phase is club 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 13 times. Then you have spade 1, 1, 1, 1, 13 times. After all these 4 keys are ready, because there are 4 different shades, we'll have 4 different keys, the reducer starts its job. In reducer, we have decided to aggregate. And in reducer, what we'll do is we'll take one key and all values for that key. So then this is what we end up getting. Add them and you get club, 13, spade, 13, and so on. This is how MapReduce typically works, where the map phase only concentrates on its own individual data. Then there is a sort and shuffle phase where all the data from all the maps is given to a phase called sort and shuffle. Then all the data is basically sorted based on the keys. So you'll have key and all the values for that key in a sorted order. Then the data is given to reducer, each key and all the values for that one at a time, and you finally get your output. So when we say it's a cluster of machines, assuming that this was machine number 1. Now, once you have all these 4 machines, each machine will have its own data here, the way you have it here.
Right.
Okay, so we'll not get into it, but let's say all of them have. Now the point is, see, every guy has done his individual job, right? Now you need some way to combine the output, right?
Okay.
So basically, we can combine output only at one place, okay? And that is decided by Hadoop, which machine will do it. Let's say in this case, Hadoop says machine 3 will perform sort and shuffle. So now map 1, machine 1 will give its output to machine 3, correct? Machine 2 will give output to machine 3, machine 3 has its output, and machine 4 also has its output.
Okay.
Machine 4 gives the output to machine 3. When all the output is given, all the intermediate data is given to sort and shuffle, all it does is it figures out the different keys. So if you see how many type of shapes are there, 4, right? So how many unique keys are there? There are 4 unique keys, right? Club, spade, diamond, and heart, right? Exactly. But the important part is this: here aggregation has to be performed. This is decided by the developer,
right?
Okay. Yeah. So this you will have to explicitly say that, hey, you know what? I want to aggregate what I get out of it.
Sure. Okay.
Okay.
The reducer can be any program actually. What you want?
It is your program. It is hardcore. So map is hardcore business logic and reducer is hardcore business logic. Everything else is a skeleton that is defined by MapReduce already. Okay. So tomorrow, let's say we had a different program where you wanted to find all the words that are occurring more than once. So you may go for the same logic, but instead of aggregating, you will see anything that is occurring twice, you put it in a separate bucket, right? So that time you will not be aggregating, you might be doing something like a filtering. Got the point?
Right. So, for a typical Java programmer or something, you probably have to decide on what actually you want to do on the mapping and what actually you want to do on the
absolutely
side, and then actually you have to think your the whole thing in that paradigm right now.
Exactly. Okay. You are just hitting it on the head, exactly the way it is. And as I said, MapReduce, the challenging part isn't writing the code. Right. Expressing all the problems in a distributed fashion is a real challenge, and that's why Hadoop is considered to be complex, because every problem so far you've been seeing in a monolithic way, you'll have to change your paradigm and start thinking in a distributed way.
Right.
Got it?
Okay. That makes sense.
And I have a question on the block size. So what determines your block size and your machine mapping? Your block size to your slave node mapping. I mean, how would you decide how big your block has to be, or how many blocks your data set is comprised of?
Okay, so the idea is this. Typically, when you install Hadoop, you'll be having 64 MB, and you can increase it to 128 MB. Now, these are two block sizes that are typically used, And as far as the mapping is concerned, it's random. So what happens is name node, now slave nodes, once they are up, they start sending, you know, what you call heartbeats to name node, where they send, you know, stuff like configuration information and how much storage space I have and all. And then name node decides which block should go to which machine.
Okay.
Okay. So you see, in this case, 52 cards. So who decided that we were going to split it into 4 parts?
Oh, as I said, it was hypothetical, if you see.
Mm-hmm.
Okay. So how it works is, let's say you have a file of 640 MB,
Mm-hmm.
right? So each block is 64 MB, right?
Yeah.
So then it automatically divides into 10 blocks and spreads it across the cluster.
Each machine will have equal number of blocks always?
That's the effort that Hadoop would make. But if you have machines in which one of the hard disk is really less, then you know that particular thing will get disturbed. You're getting the point. So Hadoop tries to get there that way. So for example, you have 2 node clusters. So that means there are, let's say you have 2 data nodes. It's a 3 node cluster and you have 2 data nodes, and you are writing a file which is 300 MB.
Mm-hmm.
That is 5 blocks. Correct?
Yep.
So 64 plus 64 plus 64 plus 64 plus 44, right? If I hope my maths is right. I was a maths failure. Mistakes, please forgive me. All right. So this is how your 5 blocks will look like. Now, if you take 5 blocks replicated 3 times, so totally how many blocks? Correct?
Mm-hmm.
Now I have 2 data nodes. Now Hadoop may, if both the machines have same configuration of disk space and everything, Hadoop may put 7 on one and 8 on another. It will do that way only. There's no other option. So basically it tries to have equilibrium, but it is all abstracted from the user. As an admin or a user, you are never going to get into those details at all, because there is something called a balancer. So assuming now that the real challenge starts here, okay, so far it is good. Assume suddenly you get more money from your manager and company and you want to have 10 nodes and you are so far having 15 blocks only, okay? Now, you will run a utility, or Hadoop at times internally runs it, it's called as balancer. So what balancer will do is, it figures out that, okay, 2 machines have this many, other 8 data nodes are having 0 blocks. Then it will start spreading it, and then you may have few machines with 1 block and few with 2 blocks. Getting the point?
Mm-hmm.
Yeah. So that's how, but that's an internal process basically.
Okay. You know, I didn't understand where the 15 blocks came from. You had 5, and then what is the 3 times 3?
Replication.
Okay.
We spoke about replication, right?
Right.
In this case, but you said 2 data nodes, so where did the 3 come from? Sorry if I'm not getting it.
No.
Okay.
See, if you go back to this thing, so everything that you write in Hadoop, okay, it replicates it by default 3 times, so that if one node goes down, other will take care.
Right. Actually, if let us say, you know, you have a mapper, and you know, from there actually it kind of send it to 3 different nodes or 4 different nodes.
Correct.
So at any given point, is that the only job actually that machine can do, or can it actually, I mean, is it like a parallel, you know, at the same time it can also accept on the...
Yes, as a cluster you can run multiple jobs provided they are not on the same data.
Oh, okay. That's
because that file then gets locked. That's about it. Yeah. I hope the cards example would give you some idea of how exactly Mapreduce works. And you know, this is how typically the real challenge for developers today is not really Java code or something. The real challenge would be, how do you express something that's so monolithic and distributed so that you can spin it on 100 machines and, you know, get your job done.
When you said like it gets replicated to each node, it's kind of distributing the blocks. So in that case, how it's, I mean, it's again against the capacity of that each node, right? So how that capacity is kind of handling that many blocks? we are distributing the data set, right? So let's
Correct.
say, like, if you go back to your example, last
Correct.
example, we have like you distributed like 13 each block, like each block will
Correct.
have 13 whatever, and so each block will be, I mean, each data node will be having some kind of capacity.
Correct.
Right. I mean, it's not like the whatever the capacity. So, and we are just distributing the same, like we are multiplying the blocks into 3.
Correct.
And each data node will have 3 blocks. I mean,
Correct.
same kind of data set. So how that capacity is getting adjusted, and is it kind of same whatever the capacity name node will have? It will be the having same capacity.
Oh, no, you that you purely decide by yourself. So see, name node is the brain. Okay.
Mm-hmm.
So it does not require lot of disk space,
Right.
but requires lot of RAM. Data node on the other side requires lot of disk and good amount of RAM because you are running programs also. Okay, it requires lot of disk. Okay, but this disk capacity is decided by administrator, purely administrator. So even if I give you 4 terabyte of hard disk, admin can decide to use only 5% of it for. So as I said that, see, when I was talking about disk space being ununiform or being a factor, the reason is administrator can decide out of my hard disk how much am I going to devote to what do you call Hadoop, and based on that your blocks would get replicated.
Yeah. And again, the 64 MB block size is too small actually, even if it's get replicated, right?
No. That is correct. The idea is this, okay? Assuming in this case, 64 MB is a small thing, that's not a problem. The problem is, the question was, are the blocks evenly distributed or not?
Okay.
So Hadoop tries to make sure that it's evenly distributed, but if not, it comes down to how much space it is there. So it is about evenness of distributing blocks. We have 30 blocks, we have 3 machines, correct? Will it always be the case that all 3 machines will have 10 blocks? Well, you cannot always say that. So this is Mapreduce. If you look at the whole flow, this is how this whole flow works. So user provides data and program, name node gets into act, and data migration starts. Data is broken into blocks of 64 MB or 128 MB. The data blocks are spread across the cluster. Once your data is in, then your job tracker gets into act and schedules the task on the task tracker. Each key value pair is processed in map phase, and then you have your reduce phase. If everything is good, we are good. If not, we get an error. That's how we are done here.